All right, so welcome back. If you read the Monday mail, then you know that there is the assignment or the schedule, I guess, for the final exam. It's we're here every day, all day long, except we get out super early on that last Friday, which is at like 2:35. So yeah, super early. So gone are the days of like get out at noon, get out at noon, get out at noon. So anyway, you can complain. I don't know if it'll work. But we're on 3.2. We're on 3.2, and we're in boogie mode. So um, remember, you turned in 2.10. Shh, you turned in 2.10 right now. And then starting this week, and I'll let you know after lunch, we'll do a little bit from the AP classroom. I'm still trying to figure out how to navigate through that website. Rolle's theorem is what this one's about, and the MVT. Okay, MVT. So we've had a couple of VT theorems, but let's look at Rolle's real quick. Rolle was a French guy. His first name was Michel or Michael, I guess. I don't know how they say that in France. Michael Rolle. Um, this was 1691, so this was like back before Disney Plus and all that stuff. Let f be a function that satisfies the following three things. This is what he noticed. He said, hey, if we have a function that's continuous on the closed interval, much like the IVT and the EVT's condition, but he said also if it's differentiable on the open, right? So that's different from the other ones, right? Differentiable in the open just means on the interior that it's continuous, there can't be any what? If it's continuous, it has to be connected, but now it has to be differentiable in the open, so no, well, it can be discontinuous, but no holes, that would still be the first one. The second one, what is an example, in other words, what's an example of where it is continuous but not differentiable? A cusp or a sharp turn or even a vertical tangent that looks smooth, right? So if it's differentiable on the open, and of course we can't have it to be differentiable at the endpoints. And then he came up with this third one. If f of a equals f of b, what does that mean? The y value at the starting point and the ending point are what? The same. If those three things happen, then here's what Michel Rolle said. Then there has to be an x value on the open interval. Can't be an endpoint where the derivative is 0. Ah, would you buy that? Yeah, yeah, because here's like a little example of it. The first example is this one. Here's a horizontal line, right? It's continuous on the closed interval. There's no holes or vertical asymptotes, and the endpoints are connected. There's no cusps or vertical tangents on the interior, and it looks like the starting y value and the ending y value are the same. So Rolle said there has to be at least one x value strictly between a and b where the derivative is 0. Do we have any of them? Yeah, how many do we have? Infinitely many, right? I pointed out 2 of them there in yellow, but there's infinitely many of them. So the horizontal line, kind of a trivial case. But it could be something like this. What goes up must come down. And because it's differentiable, it can't turn around with a sharp turn. So there's going to be at least one horizontal tangent line. And what goes down must come up, I guess, if the y values are the same. And there will be a horizontal tangent line there. Now, there could be more than one, right? There could be a lot more than one. Here's one that has 2, right? So is that kind of a revelation to y'all? Or do y'all agree with him? You have to. I mean, if you don't agree with him, then you don't know what a theorem is, right? It's a theorem. It's not called Rolle's idea, right? It's called Rolle's theorem. But it makes sense, right? It makes sense. If we start and end at the same place, and we do move vertically, then if it's differentiable, it has to turn around somewhere, and where it does, we'll have ourselves a place where the derivative is 0. What do we call those values where the derivative is 0? Critical values. Critical values. So what Rolle was saying is he was giving us the 3 necessary conditions under which we're going to have the nice critical values, because we also get critical values where the derivative is undefined, like sharp turns. But he says these are the 3 conditions you need to have the relatively nice critical values where the derivative is 0. Okay, cool. Let's try it out. Example 1. For f of x equals this on the closed interval, determine if Rolle's theorem applies, and if so, find the values that his theorem guarantees. Okay, so this is the type of question you'll be asked. Does it apply? Well, there's 3 things we have to check, right? What's the first one? Continuous on the closed. Is that function continuous on the closed? Yeah, do we have to prove it? No, we just have to say it, right? F is continuous on the closed interval from -2 to 2. And is it also differentiable? Yeah. If you don't know if it's differentiable or not, you could take the derivative and find its domain. Okay? Its derivative is going to be a cubic polynomial, which is continuous everywhere. So it is, F is continuous on the closed interval and differentiable, which of course we can abbreviate, except on Cinco de Mayo, diffable, on the open interval. And do we have to find the y values, or can we just say f of -2 equals f of 2 without testing it? Can we just assume that it's going to work? Or is there some reason to that? Yeah, it's an even function, right? F is an even function. So f of -2 is going to equal f of 2, okay? Without even having to find the value. If you want to find the value, you can. What is it? 2 to the 4th is 16 minus 8 would be 8. So if you want to equate them both to 8, that's not bad. So again, you don't have to prove it. You just have to say it. Knowing that it's an even function can allow you to equate those without actually finding it. And now, so what? Rolle's theorem applies. Rolle's theorem applies to this function on that interval. Okay, so now that it applies, his theorem guarantees what? Yeah, a location on the open interval, not the endpoints, but strictly on the open interval where the derivative is 0. So now all we have to do to find it is take the derivative, set it equal to 0, and solve. Yeah. All right, so let's do that. So f prime of x, that's going to be 4x cubed minus 4x. All right, and this one is explicitly looking for where it's 0, so we're only going to use this one time, so I'll just set that equal to 0. And that's a check. That's like 2 checks right there. One for the derivative, one for setting it equal to 0. And now we solve by doing what? Factoring out. Good. So we get 4x. That leaves x squared minus 1 equals 0. Make sure you keep it in an equation. And you can either rattle off the 3 roots from here, or you can keep going. Do we know what they are? X equals 0. And then from experience, you know the other one is plus or minus 1. Now, at this point, do you box them up, put a little blue ribbon on them, and walk away? No. What do we need to make sure of? They're in the interval. This derivative could equal 0 anywhere. We're explicitly talking about between -2 and 2. Which of those 3 values are strictly between -2 and 2? All of them, yeah. If one of them happened to be an endpoint, which is important, or outside the interval, we would toss it. If it were outside the interval, that would be kind of a no-brainer. But Rolle's theorem does not want it to be an endpoint either. So if it were an endpoint, we would toss it. And College Board has crafted equations and problems like that where you end up with an endpoint and you don't exclude it, and there's an answer choice for you that's incorrect because his theorem is talking about the open interval. And so they're testing your knowledge of the theorem. Okay? All right, so that's pretty easy, right? I mean, in the end, all we did is took the derivative, set it equal to 0. And it was a pretty easy derivative. Okay, so anyway, that was around what? What did I say? 1691? And when was Mickey Mouse's first appearance in Steamboat Willie? 28. Good. Ouch. Yeah. So that was, I guess, Mickey came after Rolle's theorem. Safe to assume. Yeah. Yeah. Okay. But you know who came in between Mickey and Rolle? Joseph Louis Lagrange. Jesus, I guess. Yeah. The mean value theorem. This is a picture of the forlorn-looking Joseph Louis Lagrange, who, if I had more posters in my room, I would probably consider putting Euler up here, of course, and maybe Joey Lewis. We're going to see Joey Lewis again later in the year, but right now, he came up with the mean value theorem, and you know what he did? This came, of course, notice after Rolle, and he took Rolle's theorem and was like, you know what? You know what, Michelle? You know what, Michelle? I understand a function being continuous on a closed interval. That's kind of an important thing. And differentiable in the open, yeah, that makes perfect sense to me. But freaking how often do the y values at the endpoints end up being the same? Like how often does that occur? I mean, it's like just by chance the y values at the endpoints are the same. So I'm going to take away that qualification, right? Because that doesn't really necessarily happen all the time. So I'm just going to go with criteria 1 and criteria 2. Now, when you loosen up the restrictions, you make a more general statement. But is it always going to be true? Joseph, not always, no. You can't just get rid of some of the qualifications and extend your results. But what he did is he effectively got rid of that third part, kept the first two, and came up with a stronger theorem, if you will. And I'll show you what I mean by stronger, because he doesn't look like he was a bulky guy. Here's what he says. This is called the mean value theorem, or the MVT for short. And you can call it MVT. All right, so mean in this case, as you're going to see, means average. Let f be a function that satisfies the following two. Continuous on the closed? Yep. Differentiable on the open? Yep. Then there is still an x value that lives where? On the open interval, okay? The other two theorems, the IVT and the EVT, the closed interval is fine. But for the MVT, we're looking for something exclusively on the interior where this happens. The derivative there doesn't equal 0, but instead the derivative will always equal this. What is this? What do we know that as? The slope of a secant line. That's what we've been calling the DQ, right? That's the difference quotient. Yeah. It's the slope of the secant line. It's the average rate of change. This is called the mean value theorem. Mean means what in this case? Average. So the derivative will not always equal 0, but it'll always equal the average rate of change. The average rate of change, the difference quotient. Okay? And you can see by the graphs here, the blue graph there is continuous on the closed from A to B. It's differentiable on the open. There's no cusp of vertical tangents. The easiest way to visualize it, the average rate of change that is to just draw yourself a secant line connecting the endpoints. And if the derivative then, which is the slope of the tangent line, is going to equal the average rate of change, which is the slope of the secant line, then visually there has to be a place where the tangent line is what to the secant line? What do we call those? Parallel. There you go. So that's your visual. It has to be parallel. So with the notability, we kind of have the ability with notability. That was a great name, notability. We have the ability to actually trace over it and then find out where it is, right? So right there. And there's one. And notice there it is. It's on the open interval. Could there be more than one? Perhaps, yes. Okay. So again, here's a blue graph. It's continuous on the closed interval from A to B. It's differentiable on the open interval from A to B. The average rate of change, you could draw that. Now you visualize your secant line, and you don't even have to like draw it and trace it. You could visualize it, right? Here's 1, and here's 2. This makes a good multiple choice question. It could say, given this graph without the secant and tangent lines drawn on the interval from A to B, how many values of x satisfy the mean value theorem? And the answer for this would be what? 2. That's a pretty easy multiple choice question if you know what you're looking for, yes? Okay. Let's do one. No, 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 no. Okay. There's a function that's continuous on the closed interval from A to B. How many values satisfy the mean value theorem? If you want to just kind of mimic it, you can draw something similar. How many values on that interval from A to B satisfy the conclusion of the MVT? How many? Makes a great multiple choice question. If you write it on a card, it makes a great stocking stuffer for a special someone. Yeah. Yep. It's like a receipt of their taxpayer dollars, what that is. How many of y'all say one? We're guaranteed one, right? We're guaranteed one. Could we have more? Sure. Who's got an answer? Five? Five? Yeah, and you don't even, you could probably visualize it, right? There's the secant line. Look at that. Okay, so I'm just going to move it around. Ready? Okay, so there's one down there, right? One. Slide it as you go from left to right. There's two. There's three. There's four. There's five. Five is the answer. Pretty easy question if you know what to do. Okay, now let's look back at poor rolls because we don't really talk about roll anymore because we have Lagrange, Joe Louis. Do we really need Rolle's theorem now that we have the MVT? No, because if you happen to have that special case where the y values are the same, let's go ahead and do the mean value theorem. If we draw the secant line that connects the endpoints, what type of secant line is it? Horizontal. The average rate of change would be 0. So by the mean value theorem, there has to be at least one place where the average rate of change equals the instantaneous rate of change. So it turns out that Rolle's theorem becomes nothing more than a special case of the mean value theorem, the MVT. Okay? So sorry, Rolles. Now, it would have been funny if Rolle came after Joseph Louis Lagrange, right? If Lagrange came up with the mean value theorem and Rolle's like, yeah, but in the one case where that's it, I'm going to call that my theorem, right? But that's not how things progress, right? Rolle was kind of the pioneer, came up with these qualifications, and then Lagrange loosened up the restrictions, and now we have Rolle's mean value theorem. We don't really talk about Rolle. In fact, Rolle is not on the AP exam anymore, but I always feel like I need you to know about the original pioneers. So Michel Rolle, I don't think there's a poster of him out there, okay? You can Google image search him, and I don't even know if a picture will show up. It's kind of like we don't need the Pythagorean theorem anymore, right? Because we have the law of cosines. It's kind of the same thing, right? But we still talk about Pythagoras and how he came up with the theorem and didn't eat beans and killed Hippasus. What? Oh, well, I mean, maybe you teach them Rolle's theorem, and by the time they get to the high school, then you teach them MVT, right? I don't know. Okay. Because the law of cosines, remember, doesn't work just for perfect right triangles, right? How many of us are all born perfect right triangles, right? How often are the y values the same? Not very often. So the law of cosines works for all triangles in power hour, baby. Okay? And the MVT works for all continuous functions on a closed interval and differentiable. Hey, what if it was continuous on a closed but not differentiable on the open? Does the MVT apply to this sucker? I didn't mean to call him a sucker. Fella? Does the MVT apply to this fella on this interval? No, no. Now, can we have a place where the average rate of change equals the instantaneous rate of change? Can we, in theory? Yes, but is there a guarantee? No. Does this one, in fact, have one? There's the secant line. Let's see. Let's move it. And now it's like what? Is that a tangent line up there? Whoa, it's a seesaw. It's precarious. Whoa, accident waiting to happen. Nope. No. See? So that's why it has to be differentiable on the open. Okay? All right. I didn't get many cold milk guys sent to me, and I can't find the folder of my old ones from like 10 years past. So I'm having to start a new milkman collection. If you want to like make it a Joe Louis, you can. All right. Example 2. Ready? Example 2. How are we doing on lunchtime? 7 minutes. This is the type of question you'll have. Okay? Guaranteed. Determine if the MVT applies to this function on that interval, and if so, find the value, or look at this foreshadowing, find the value or values. Ooh, could be more than one. Guaranteed by the theorem. Was that a duck? All right. So here's what you just tell yourself. You don't have to prove it. You just have to state whether it is and then state why. That's a polynomial. It's a cubic polynomial. It's continuous and differentiable where? Everywhere. So we just have to say f is continuous on the closed interval from 0 to 2 and diffable on the open interval from 0 to 2. So MVT applies. That's it. That's basically testing. Do you know the two requirements for the MVT? Okay, that's what that's testing. Don't say F is continuous and differentiable everywhere, therefore the theorem applies. That's true, but that does not speak to the theorem specifically, all right? And maybe your handwriting is better than mine. I hope so, okay? All right, so now what do? Well, we need to find the derivative, and instead of setting it equal to 0 in solving, we'll set it equal to the average rate of change. Now, here's a good way to set it up. I would recommend highly that you do this step every time. The function's name is f, okay? So I'm going to say f prime of x. If it were g, I would call it g prime. And it's going to equal f of 2 minus f of 0 all over 2 minus 0. So you're doing it kind of symbolically with the function notation first. And that is going to earn you a check for your setup every time, okay? Now let's go ahead and compute it. What is the derivative? Well, it's 3x squared minus 1. And now, gosh, what do we do on the right side? Plug and chug, baby, right? Plug in a 2 and you get 8 minus 2. Well, that's 6. Plug in a 0, you get 0 all over 2. So 3x squared minus 1 equals 3. So this function, on average, as it moves from x equals 0 to x equals 2, on average, goes up 3 over 1, up 3 over 1. That's probably not how it actually gets there, okay? It gets there through a variety of rates. But it has to be 3 somewhere because the function's continuous and differentiable. So now we can solve, and for this one, how would you do it? How do we solve this one? Bring the 3 over? Yeah, we would separate it, right? Because there's only one variable, so 3x squared would equal 3 plus 1 is 4. X squared would equal 4/3. And we take the square root, and when we do, we can't forget to remember to do plus or minus. Now remember, we're talking about a theorem. We're not just finding anywhere on the graph where the average rate of change is 3. One of those is supposed to be on our interval, but they both could be. Are they both in our interval? No, and it's pretty clear without a calculator, right? We're going from 0 to 2. We have a negative value. The other one then, I guess, this one is out. You can exit like that. Or there it is. Show that it's not in the interval. And or box this one. We don't really know what that number is, but it's the only one that's left. And because of the theorem, we know it has to live somewhere between 0 and 2. Now, if this were a multiple choice question, would there be an answer choice that has both of those as answer choices? Yes, yes. And it may not be in that form. So let's think about another version of the square root of 4/3. That's the same as the square root of 4 over the square root of 3. That's the same as 2 over the square root of 3. So that could be the answer. If you rationalize that, you get 2 square root of 3 over 3. So that's yet another version of it. Okay. If you multiply it by 17 over 17, you get, no, they wouldn't do that. Okay. But any one of those could be the answer. On a free response, are you going all the way to 2 root 3 over 3? No, no. If you said yes, that was funny. I get it. No, you're not. You're stopping at square root of 4/3. Okay, so that's the mean value theorem. You know what it looks like visually. You know how to work a problem computing it. We will do example 3 after lunch, and we'll do it with a calculator. So if you have a calculator or you want to grab one when you come back from lunch, that'll be example 3. Okay? Mean value theorem. Very, very important.